Back in school, most of us memorized one line without ever really asking why. A squared plus b squared equals c squared. We used it to pass a test. Maybe to figure out how long a ladder needs to be to reach a window. Then we closed the textbook and forgot about it. But did anyone ever tell you why it has to be squares? Picture the classic drawing, a right triangle, and on each of its three sides sits a square. The two small squares always add up to the big one. Simple, right? Now imagine we swap those squares out, put a circle on each side instead, or an equilateral triangle, or even something playful, like a little fish shape, repeated 3 times at 3 different sizes. Would the two small areas still add up to the big one? If your gut says yes, you're closer to the real theorem than most people who memorized it in school ever get. What if the square was never the point? What if it's just one tiny, accidental example of something far bigger? Let's reopen the case. Here's the trick our schools pulled on us. They taught the Pythagorean Theorem as a tool for finding a missing number. Plug in 2 sides, get the third. Useful, but that's not what the theorem is actually about. Go back to that picture again. A right triangle with a square built on each side. Now imagine you could physically cut up the 2 small squares into little pieces and pour every piece into the big square, like sand. If the theorem is true, those pieces fill the big square exactly. No gaps, no overflow. That's the real claim being made here. It was never really an algebra formula first. It's a statement about space itself staying balanced. The ancient minds who first noticed this weren't thinking in equations. They were looking at physical area and seeing that it never got created or destroyed, only rearranged. If you ever looked at that picture and felt like there was something deeper going on than just multiplying 2 numbers together, you were right. But before we can unlock why this holds for any shape at all, not just squares, we need to see how humanity actually stumbled onto this idea. And no, it did not start with a Greek philosopher named Pythagoras. Long before Pythagoras was born, a clay tablet was already carrying this secret. It's called Plimpton 322, and it was written in what's now southern Iraq, in the ancient city of Larsa, somewhere around 1800 BC. It was dug out of the ground in the early 1900s by an archaeologist named Edgar Banks, and today it sits in the Rare Book and Manuscript Library at Columbia University. The tablet is a table of numbers, carved in wedge-shaped cuneiform script. One of its rows lists 3 numbers, 12,709, 13,500, 18,541. Square the first 2, add them together, and you land exactly on the square of the third. That's a working Pythagorean triple, written down more than 1,000 years before Pythagoras walked the earth. The Babylonians weren't doing this for philosophy. They were surveying land and digging canals. They needed right angles that actually held up in the real world. Centuries later, in the 6th century BC, Pythagoras and his followers turned numbers into something closer to religion. None of Pythagoras's own writing survived, so historians still debate how much of the proof was really his. What we do know is that the question of proving this relationship, once it took hold, became an obsession that outlived him by thousands of years. Around 300 BC, the Greek mathematician Euclid gave the theorem its first fully written, rigorous proof as Proposition 47 in Book 1 of his work called Elements. That obsession never really stopped. In 1940, a mathematician named Elisha Scott Loomis published a book that collected 370 completely different proofs of this one theorem. 370. Why so many? Because each proof is really a different way of looking at space. Let's look at the most famous one and find the logical trap that almost everyone walks right past. Take four identical right triangles, each with legs A and B and a hypotenuse C. Arrange them inside a big square whose side length is A plus B. Push the triangles toward two opposite corners, and you get two empty patches left over. One patch is a square of side A. The other is a square of side B. Now slide those same four triangles into the other arrangement, tucked into the four corners instead. This time there's only one empty patch left, sitting in the middle, and every one of its four sides has length C. Here's where almost every version of this proof quietly skips a step. How do you actually know that middle patch is a square? Just because its four sides are equal doesn't prove it. A rhombus also has four equal sides, and its corners are nowhere near 90 degrees. So let's prove it properly, using nothing beyond what you learned in school. The three angles inside any triangle always add up to 180 degrees. Our triangle already has one 90-degree angle, so its other two angles have to add up to exactly 90 degrees. Now look at one corner of that middle patch. It sits on a straight line, and a straight line always measures 180 degrees. That straight line is made up of three pieces. One of the triangle's small angles, then the corner angle of the middle patch, then the triangle's other small angle. The two small angles already add up to 90 degrees, so the corner angle of the middle patch has to be the remaining 90 degrees to make the full line equal 180. Every corner works out the same way. Four equal sides, four right angles. That middle patch really is a square, not just a shape that happens to look like one. It might feel like we're nitpicking over one angle. But that one angle is what turns this from a nice-looking picture into something mathematically bulletproof. Still, this proof leans entirely on squares. To see why the theorem reaches far beyond squares, we need to look at the triangle itself in a completely different way. Draw one right triangle, call its right angle corner C, and the other two corners A and B. Now drop a straight line from corner C down to the opposite side, hitting it at a perfect right angle. Call that landing point D. That single line just split your triangle into two smaller triangles. Here's the strange part. Both of those smaller triangles are just shrunk-down copies of the original one. Same three angles, just smaller. Rotate them in your head and they slide perfectly onto the big triangle's outline. Let's put numbers to it, using the most familiar right triangle there is. Sides of 3, 4, and 5. The hypotenuse is 5. When we drop that line from the right angle, it splits the hypotenuse into two pieces. One piece measures 3.2, the other measures 1.8. Check the math and they add back up to exactly 5, because the smaller triangle on the left is a shrunk copy of the big one. Its sides line up in the same ratio. The short piece, 3.2, relates to side 4 the same way. Side 4 relates to the full hypotenuse, 5. Written out, 3.2 divided by 4 equals 4 divided by 5. Cross-multiply that and you get 4 squared equals 5 times 3.2, which is 16 equals 16. The same thing happens on the right side. The piece measuring 1.8 relates to side 3 the same way side 3 relates to 5. That gives us 3 squared equals 5 times 1.8, which is 9 equals 9. Now add those two results together. 4 squared plus 3 squared equals, on the right side of the equation, 5 times 1.8 plus 5 times 3.2. Factor out the 5, and that's 5 times the sum of 1.8 and 3.2, which is just 5 times 5. 9 plus 16 equals 25. And 5 times 5 also equals 25. That's not a coincidence dressed up in numbers. It works for any right triangle, because the two smaller triangles are always shrunk copies of the big one, no matter what the actual side lengths are. There's something worth sitting with here. A squared plus B squared equals C squared is really just two rectangle areas, created by projecting each leg straight down onto the hypotenuse, added back together. But look closer at that equation. Why squared specifically? Because in the world we live in, area is tied to the square of length. That single fact is the key that unlocks this theorem for shapes far stranger than squares. Here's a fact most of us never stop to notice. Every flat shape's area comes from the same underlying pattern. Take some length that defines the shape, call it L, square it, and multiply by a constant that depends only on the shape. A square with side length L has an area of exactly L squared. Its constant is just 1. A circle with diameter L has an area of pi over 4 times L squared. That constant works out to about 0.785. An equilateral triangle with side length L has an area of the square root of 3 over 4 times L squared. That constant is about 0.433. Different shapes, different constants, but the same underlying pattern. Area always scales with the square of length. Now go back to our right triangle, with sides A, B, and C. Instead of building squares on each side, build any shape you like, as long as it's the same shape at 3 different sizes. Circles, equilateral triangles, even that fish from earlier, because all 3 shapes share one constant. The area sitting on side A is that constant times A squared. The area on side B is the same constant times B squared. The area on side C is that constant times C squared. We already proved A squared plus B squared equals C squared. Multiply both sides of that equation by the shared constant, and the area on side A plus the area on side B equals the area on side C. The squares were never the point. This is a law about how space itself scales. Draw 3 fish, all the same shape, size to match the 3 sides of a right triangle, and the 2 small fish always add up to the big one. This isn't just a modern reframing either. Around 440 BC, a mathematician named Hippocrates of Chios used this exact scaling idea on shapes bounded by curves. He built 2 crescent moon shapes, called lunes, on the 2 legs of a right triangle, and proved their combined area equals the area of the triangle itself. It was the first time in recorded history that a curved area got measured exactly, using nothing but a straight-sided shape. The idea doesn't stop at flat shapes either. In 1783, a French mathematician named Jean-Paul de Goua de Malves published a 3-dimensional version. Picture slicing one corner off a cube, so you're left with a pyramid-shaped chunk that has a perfect right angle at its tip. The square of the area of the slanted face equals the sum of the squares of the areas of the 3 faces meeting at that right-angled tip. To keep things intuitive, we're staying inside flat space here. Warp the space itself, like drawing a triangle on the surface of a sphere, and this scaling law breaks down. Pythagoras stops holding. But in the flat universe we actually live and build in, this scaling law is absolute. From flat shapes to 3-dimensional corners, from straight lines to curved moons, this was never a pile of separate rules about triangles and squares. It's one truth about how our universe scales. So the Pythagorean theorem was never really a formula to memorize for a test. It's closer to a physical law, describing something true about the structure of flat space itself. The moment we stop treating math as a random pile of rules to be memorized and start looking for the intuition and the scaling underneath it, the whole subject opens up into something genuinely beautiful. Mathematics isn't a stack of arbitrary conventions someone invented and we all agreed to follow. It's a tightly connected system where nothing sits alone. The logic underneath never changes, only the tools we use to see it do. If there's another one of these school memories still haunting you, sine, cosine, logarithms, whatever it is, tell us in the comments. That might be exactly what we dig into next. And if you want to keep chasing these hidden truths with us, stick around on Axiom Code.